Devices on a network commonly use both IP addresses and MAC addresses to communicate. But how do devices know which IP addresses go with which MAC addresses? This is possible due to a protocol called ARP. And in this video, we're going to see what it does and how it works. Think about the OSI model. There are several layers which need to work together to get from one host to another. Frequently, IP addresses at layer 3 are used to identify which device to send traffic to. But there is also a layer 2 path to follow, and devices at layer 2 use MAC addresses. Imagine that you have two hosts within the same subnet. Perhaps one is a web server and the other is a client. The client knows the IP address of the web server and wants to start an HTTP session. So the client builds a TCP segment and encapsulates it in a layer 3 header. It needs to add a layer 2 header as well, but what destination MAC address can it put in this header? Right now, it has no idea. It simply does not know the destination MAC address. And this is where Address Resolution Protocol comes in. The whole point of ARP is to find the MAC address that belongs with an IP address. ARP works by sending a layer 2 broadcast message to the entire LAN. This message is called an ARP request. The request contains the statement, "Who is 10.10.10.21? Tell 10.10.10.44. All the devices on the LAN will get this message. They will look at the IP address in the request and see if it is their own. For most of them, this will not be their address, so they will discard the message. But if the device we're looking for gets the message, it will then create an ARP response. The response will contain its own IP address as well as its MAC address. The response will be sent as a unicast message only to the host listed in the original request. Now that the client has its response, it will put this information into its ARP cache. This is a small table that contains all the IP to MAC address mappings that it has learned so far. Caching is done, so there will be no need to send an ARP request for every single packet that it needs to send. These entries aren't permanent though. Over time, if the entry is not used, it will be removed from the cache. To give you a rough idea, a modern version of Windows will store an ARP entry for somewhere between 15 and 45 seconds. There are two reasons for this. For one, there is limited space in the ARP table. Clearing out stale entries helps keep the table small and organized. For another, devices sometimes change their IP addresses. If the ARP cache entry had an indefinite lifetime, one device may have trouble noticing another's IP address change. We can see this from the Windows command line. This here is its ARP cache. You can see all sorts of entries in here. Now if we ping something new, Windows will need to send an ARP request to find the MAC address to IP mapping. And this usually happens very quickly. And if we look at the ARP cache again, we can see a new entry has been learned. In addition to regular ARP, there is also RARP and GARP. RARP is reverse ARP, and it does exactly what it sounds like. If a device knows a MAC address and wants to find an IP, it will send a RARP request, and the MAC owner will send a RARP reply. The really cool one is GARP, or gratuitous ARP. Remember how I said before that IP addresses can change? Ideally, we don't want to wait for the ARP cache entries to expire before we learn about these changes. So if a device has good manners, it will send a GARP message when it's changing its IP. This is its way of announcing its new MAC to IP mapping to everything on the local network. This isn't the only time this happens. When a device first boots up, it will also send a GARP message. And this has two advantages. Firstly, devices learn the IP to MAC mapping for the new device without needing to send an ARP out. Secondly, if the IP of the new device is already in use, the device already using it can send a GARP reply. This helps to prevent IP conflicts.